Hey, Sean. Can you hear me, Sean?
Yeah, I can. How you
Okay.
doing?
Awesome. Awesome. I'm well. Hey, Eric.
Hey, how's it going? You guys hear me okay?
Yep. Hear you loud and clear. Doing well.
Yeah. I assume you can see my screen.
Yeah.
All right. So I haven't participated in the. All right, I'll be right back.
Okay. Well, I assume, Eric, that you don't see across the top of my screen where it says your screen sharing and all that kind of stuff across the top of the screen.
I do not.
Okay. Because what I'm seeing on top of the slides is that Zoom, bar.
Oh, yeah. No, I don't see that.
Yeah, okay. I wouldn't think you would, but
Has TRM done a grid before?
we have. Um, Eric has not done one, but I did the first one.
Okay.
So I assume then that at 11 o'clock you'll let everybody in.
Yep, I'll start it.
Okay. And then once we're done, I'm sure that you gracefully close it.
That's correct. Yep. I'll thank everyone for coming and remind everybody to tune in September for our next in the series of
Yep. Our next TBD.
yeah, our critical engagement.
Yeah.
Uh,
So that page up in that page, make sure it's all active. Good. So Jason, did Bailey give you any indication as to once you let everybody in, how long we should give them a little bit of dead air before I start?
She did not.
Okay.
Um,
So, give them like, I don't know, 10 or 15 seconds, I guess, just give them something to let them, log in and wherever they gotta do with their systems to get sound and all kind of stuff, or.
okay, yeah. Do you want me to start it now then?
No, I mean,
Or
this,
start at the top of the hour?
yeah, right, what we did last time, we started it right, pretty much exactly on time.
Okay,
But what I'll do then is, because as soon as it starts, then, the three of us will be live, right?
I
Uh,
believe so.
Yeah, so
You're more experienced than I am.
yeah, so what I'm gonna do, just so you're aware, is let me know when you're opening up the floodgates.
Okay,
And then once, because I think once that happens, I'll get a notification here that the webinar started. And as soon as that starts, then I'm gonna wait like 15 seconds, and then
perfect.
then I'll start the intro.
Okay. Sounds good.
I just want to make sure that we don't actually start it before people are actually, fully, in the room.
Yep, understand.
You know what I mean? I forget what she did last time. Whatever she did worked out pretty smooth, because but I forget those details.
Okay. All right, got about a minute to start.
Yep.
All right, I'm starting it.
Yeah. Hello, everyone. I'm Sean Moore, Chief Technology Officer at Quantic TRM. Welcome to The Grid by Quantic Electronics, a monthly platform that connects engineers to critical insights. This month, The Grid features panels from Quantic TRM. Quantic TRM is a provider of high reliable passive microwave components for defense and space markets. Quantic TRM partners with our customers to offer them the best passive RF solution. Our core products of power dividers, directional couplers, and hybrids can be offered in custom configurations or integrated into subsystems that are tailored to your exact requirements. We also perform the testing and deliver the data for a superior total value for the program. In today's webinar, you will hear from myself, and Quantic TRM's Director of Engineering, Eric Zumiez. I'd like to start off the presentation with a brief overview of what we're going to be going through today. And basically, we're going to start with a brief introduction. We're going to go through what I like to call the requirements list as far as what we have for trying to determine what is really critical when designing components. This is a discussion on what you absolutely have to have for the system to do what it needs to do, and also what is nice to have for additional other parameters going on. We'll then go through a whole series of performance trade-offs and how those trade-offs can affect your cost, your lead time, and other performance parameters. I'll give you a very brief overview of Quantic TRM, and we'll wrap it up with a summary. So to start off really with this discussion, it's really all about what is a need to have versus a nice to have. And to kind of clarify and set kind of a definition here, the need to have parameters are things that are critical specifications that will affect overall system performance. For a receiver, for example, that could be insertion loss or noise figure, things that can actually go in there and limit the range of the system. There are lots of parameters in there, and we'll get into some of those in a little bit. Nice to have parameters are things that, and some examples that I'm going to give here are things that would make it more convenient, but won't necessarily improve the overall system performance. For example, it's very often, if you're a system engineer, you like to reduce the number of individual part numbers in the system. And if you're going to put the same device in multiple locations of the system, that can be a nice thing to have because it will help with management of some of your inventory. The downside of that, we're going to get into in a little bit. Also, adding some additional either bandwidth or other capabilities for possible future upgrade variants. Again, those sorts of things can go in there and can have an adverse effect short term on your need to have on your need to have parameters. In addition to that, sometimes putting guard bands onto components can go in there and actually have a negative effect on your overall performance. So these are the sorts of things that we're going to talk about today to really find out really what's important, what isn't important, and as we're going through there, have you come up with a more intelligent way of specifying components so you actually end up with the best performing system overall possible. And kind of going through now a little bit of detail now as far as to what we have versus the need to have versus nice to have performance parameters. Part of this has to come into if we're looking at, for example, putting a component in multiple locations. Very often that requires a broader bandwidth sort of component. If you have one component that is working down, say, for example, at the low end of X band, and another one maybe working at the low end of KU band, those could be two different components, or they could be combined into a single broader band type component. What happens with dealing with passive microwave components, and you can think about this very much as trying to squeeze a balloon. If you try to increase the performance in any one area, you will decrease it someplace else. There are physical constructions that go on, especially with a lot of the distributed sort of designs, where there are inherent bandwidths with any one of these overall distributed structures, or with the overall lumped element type structures, depending what frequency band that you're working in. So what we have here really is, and to give some good solid examples here, a typical bandwidth of a lumped element construction, where this is a transformer and capacitor-based sort of power divider or directional coupler, you typically can get about 100 to 1 bandwidth. Now, the thing with this over here is with that much bandwidth, you can usually have good performance over a variety of bands. You do to have a penalty up at the very high end of that bandwidth, usually with insertion loss, over what you would get for a narrow band sort of divided for lumped element sort of designs. So lumped elements are sort of an anomaly in the discussion of what we're going to have today. But I will say that there is definitely a trade-off that needs to be made when you start going to extreme bandwidths. And we do have some customers that are interested in getting involved in some of these extreme bandwidths. Distributed aligned technology is very much based on on the Chebyshev polynomial, and in doing so, there is a definite bandpass sort of structure here that is in play. And what we get here for typically is that for a distributed transmission line sort of transformer, which is the basic building block for a lot of the directional couplers as well as power dividers, a single section transformer will get you about a 20% bandwidth. A 2-section transformer will get you about an octave, and a 3-section will get you about a 3-to-1 bandwidth. So what happens here is that if you're trying to go, say, for example, say you're trying to get very good performance at X band, and you have something down at C band and something up a KU, you can get those into a single device if you have a 3 or 4-section transformer. Well, what this does here is that at the more length that you add to the transformer, the higher the insertion loss that you're going to have, especially up at that higher band. Depending on where it is in your system, that insertion loss might really degrade the system, and therefore a nice to have parameter, for example, of having a single device in multiple locations of the system can actually degrade your performance. Having this discussion with a vendor like Quantic TRM can very often help you mitigate those sorts of performance issues going forward. Other things that you have going forward with adding sort of bandwidth to these sorts of products in addition to the higher insertion loss is that you have an increased circuit complexity. And as you start adding more and more components to an individual circuit, your reliability can drop. Every time that you have a step in a transformer, going back to the transmission line design, you will have a corresponding degradation that is going to happen in VSWR. The more elements you have, the more opportunity you have for reflections to happen. That will probably also degrade your overall isolation, and it will certainly make for a larger physical mechanical package. So when looking at putting a single device in multiple locations, these are the sorts of things that we need to consider going forward to make sure that really what you end up with is an optimal performance, and not necessarily going in there and looking at what would be nice to have for the system. Now, on the other hand, if your system and with where these components are going in the system, you can tolerate these sorts of penalties, then by all means, we can go ahead and talk about going with a broader band sort of component. Lots of options are available here, and with dealing with a custom manufacturer like Quantic TRM, we're happy to go through and discuss all these trade-offs with you to make sure that really what you end up with is an optimum package for what you're looking for. Another common place where we see these trade-offs happening is in power handling. Power handling, again, like bandwidth, is not always free. There are certain physical constructions where you will have a nominal sort of power handling capability, and within those sorts of ranges, there really is no penalty. And understanding where that threshold is, getting up to that next level of power handling is quite critical in understanding really when you write specifications. This is extremely critical once you start looking at parts, for example, they're going on a spacecraft, or if you're going on some very high altitude sort of applications, where you have to worry about things like a multi-pactor failure, which is a resonant sort of breakdown sort of phenomenon, or a critical pressure corona breakdown. These sorts of things also will determine a lot of our design criteria with products, how we actually go in there and deal with the line to ground spacing, as well as our dielectric geometries and those sorts of things. The other thing also that it's really critical to look at is the thermal management, going through and looking at how much heat can we transfer through any one particular construction device. A good example there is that if we're looking at a power divider, for example, where we have a higher power throughput on it, very often we have to change the PCB material from there off of a Teflon dielectric board up to a ceramic loaded board or other sort of a material. And in going through there, what happens there is that instead of going from a very low loss material, in order to get the better thermal performance, we actually degrade the overall insertion loss. It becomes a trade-off between power delivered to the load versus how much power is dissipated in the device and how much heat we can get out of the device. There is a teeter-totter sort of effect that happens there that at some point we do actually have to take an assertion loss penalty in order to be able to conduct more heat. And these is another trade-off that we routinely work through as we're going through these higher power devices. Also, once we get into higher power devices with larger components that'll handle more power, we do have an increased interaction with the parasitic effects of the individual components. Resistors, for example, have a significant amount of shunt capacitance associated with the terminations and the physical size of the resistor film. As those get larger, those capacitances creep more and more into the design and actually detunes the circuit to the point where we then have to start making additional modifications within the circuit itself to compensate for these stray capacitances that happen. The direct result of that is that we decrease the effective bandwidth of the device, even though we have the same number of sections as a lower power device. Another important trade-off to look for to really see whether just arbitrarily saying that, gee, I want the part to be able to handle 30 watts, where in reality it's going to see 100 milliwatts. That can dramatically change the way we design the component. It'll actually hurt the design going forward in the long run for a nice to have parameter that you will probably never use in the actual application of the device. In addition to that, parts with higher power are usually quite a bit larger, just to handle the thermal transfer, and they do get heavier going through there. I'd like to now pass it off a little bit to my partner Eric, and talk a little bit about the next couple of trade-offs that we need to do.
Yeah, thanks, Sean. So looking specifically at the mechanical approach and working with customers on supplied outline drawings as an example, overly constrained size requirements, trying to really squeeze the amount of size that's available for these components to live within. Like as Sean just was talking about, it'll drive the style of topology that they put into the electrical design, which has its own trade-offs. It'll also force the mechanicals to squeeze and get away from standard overall structure shapes and to try to squeeze into fit to these smaller areas. So it's always best, work with us to understand the design approaches we would take. We happy to supply outline drawings at the front end of quoting stages to let you know where we think designs are going to land. Obviously, there's exceptions and things just need to fit in small spots, but there's always a trade-off there that can get looked at. The connector choices, every connector, there's a lot of factors that go into which connectors to be picked. Just from a physical standpoint, mounting a connector onto an assembly, whether it's a thread-in connector or a press-in, or if you have a 4-hole flange or a 2-hole flange, each one of those has its own trade-offs, and then they also come with their own physical size needs to be able to be incorporated into the design, and that needs to be taken into consideration also. Frequency limitations, right? If we're specifying a part that's going up to 22 gigahertz, but we have SMA connectors on there, that's the SMA capping out around 18 gigs, that's going to be an issue. So understanding the true scope of where this product's going to be used and how far up in frequency or how low in frequency it's going to be operating at, and making sure that the right connector is selected so we don't have issues during the design and testing and tuning aspect of the builds. Power limitations of smaller connectors. Sean was talking about breakdowns and internal features that we can incorporate into our design. But oftentimes what will end up happening is it's the RF interface where the breakdown will occur. We can mitigate it from the internals out, but if the wrong connector is selected for the application, the breakdown could actually happen within the RF interface. So it's important to select the right connectors based on power requirements as well. And then there's also phase stability and isolation concerns when it comes to the blind mate style SMP, SMPM type connectors. Test stand repeatability, all those, it's not as robust of a mate as a nice threaded or bayonet type connector. So there's trade-offs there that need to be taken into consideration that could drive longer lead or tune times here at the factory. Finishes, so non-standard finishes on the outer component itself. The typical industry standard being the milled DTL 5541 iridite finish on the aluminum housings is very classic, very typical. You start getting away from that, you into more of the nickel plates or the gold platings. A lot of those are outside operations. They have their own lead times and handling concerns. Less touch-up ability when it comes to those types of finer finishes. So there's trade-offs there. If nickel plating is not truly a need, then maybe the standard mill DTL would satisfy. And also painted parts. If we're dealing with painted surfaces, but we have some really tightly toleranced connector locations or connector offsets, but they're being toleranced off of painted surfaces, that poses a problem as well. So it's understanding how datums are being set up and how certain things are related to these painted surfaces that will not be able to hold the tight tolerance as a nice smooth machined surface. Taking those into account while laying out the mechanical outlines. Reliability requirements. This is something that we deal with often. So we're trying to do, we're trying to specify some components for resistors and capacitors. And if it's dictated that we have to use a failure rating of an S level chip, which is, space level, T levels, those types of chips, they come with a cost and a lead time associated with it. So if it's not a true need and either a commercial resistor or capacitor would work, or even just a lower rating R level, you could be taking a 2-cent or 10-cent resistor chip and making it into a $15 resistor pretty quickly, and then adding on weeks of lead time for those screening tests to be performed. So understanding the true ratings that are being called out and making sure that they are actually required goes a long way. And that applies for connectors as well. Connectors can get screened to mill standards. So it's just understanding those trade-offs where there's going to be a cost and a lead time impact to get those types of components in. MTBF, or mean time between failures, that this is an interesting one where we'll see a variety of times given, of desired times that they would like to have. So understanding the true mission life and where these components are going, whether it's a 15-year or 100,000-year type test or requirement, will drastically dictate how the design is approached. Right, the higher in that MTBF value, we have to start removing solder joints, removing components to really get it down to as reliable of a trace as we can. So all those little added features will hurt your reliability factor. So we start getting into some non-standard, very customized solutions. Certainly able to be accomplished, but there is a lead time and cost associated with that. So that's just something to be aware of. If rather than just picking a really high value to play it safe, it's really understanding what the true need is, because that will impact how the design is approached. And then environmental impacts. So material selection, outgassing, vented versus sealed. Those first two bullets are, think about space applications. If at the next higher level assembly, if our component is going into a hermetically sealed subassembly, then maybe the same sort of sealing requirements are not needed to get pushed down into our part because it's protected at that next higher assembly. So understanding kind of where it's going in the system, and rather than just flowing down the same specifications, maybe there's some leeway in there to allow for other components to be used. The outgassing, as an example, really knocks off a lot of our sealing epoxies and other components like that. So it's important to really understand what those are driving. And then you go into the types of seals, and a basic environmental seal for say humidity or sand and dust is going to be different than if you're trying to seal up for salt fog atmosphere, where you're going to want more of a gross leak level seal. But if you're looking for just basic humidity and storage type of a seal, to specify a gross leak or a full hermetic seal is definitely overkill. And both of those will have a different design approach and will have an impact to, again, cost and lead time and testing and validation that goes into those. And then mounting is another big one. Mounting is often, I'm talking mounting of the R component to the next higher assembly. And oftentimes that's dictated within the customer supplied outline drawing. So it's making sure that when mounting is provided and those mounting points are defined, that they are adequate enough for the environment that they're scheduled to be tested against. We've had instances where the mounting hardware was not sufficient and actually snapped during the environmental testing of vibration or shock. So the parts themselves will pass, but the mounting that was designed at the beginning to hold them down was not adequate enough. The wrong size was selected. So understand that if that is going to be dictated and passed down, that there's some thought into the next layer of environmental testing that it needs to survive. And then right into environmental testing. So there's costs associated with every environmental test and lead times. We have a pretty decent selection of test abilities here at TRM. We do utilize outside shops to do the ones that we cannot. And a lot of the cost drivers that we see is when you have these specialized operational type environmental tests that are required. So if we're going out and doing a thermal vacuum test, we're doing a TVAC chamber test out at an outside supplier, we need to bring all of our equipment. We need to make sure we have custom fixtures and jigs made up so that we can supply all of the operational equipment to the unit within whatever chamber that they have available for us. We need to have operators there running the equipment. It's long lead times, a lot of costs associated with the testing itself, and can really add tens of thousands of dollars in just the testing alone of the units. And then lead times is also extensive, being if it's an outside shop that we're utilizing, working within their schedules, understanding that different ratings of jobs can come in there at any point. If a DX job comes in, our parts get kicked off and we have to wait until the slot opens up again. So there's a lot of, so the longer the test that we need to have that window blocked off, the more risk there is of that happening. So it's really understanding what the true need of the environmental testing is. Will a non-operating test achieve the same risk reduction validation that an operational test would do? Those are just trade-offs that should be considered when laying out the test plans and the test requirements of these units.
All right, thank you, Eric. And basically, I'm going to kind of summarize up here a little bit as far as what we've been discussing today. Basically, we have the nice to have requirements, which are things that are, can be very safe. In addition to that, these are things that that are things that we can have and think about them as future opportunities, or just in general, just being safe without having to actually think too much about it. Versus the actual performance that we actually have to have for the need to have performance of a component. Understanding the impact of every parameter that gets put on us as a manufacturer does affect your cost. It does affect your lead time, and actually by putting more requirements on there that are not actually required or could actually adversely affect the overall system performance. So things that we spoke about here today are things like just basic electrical performance with these sorts of components. For passive microwave components, we're looking at insertion loss, VSWR, isolation, those sorts of things. How bandwidth goes through there and impacts those individual parameters. Power handling, thermal management, overall package performance. I think a lot of things that people don't tend to always think about. Gee, the box that I'm going to put this component in will affect its performance. It absolutely does, and these are things that we need to consider as we're going through and building up the overall packaging up into the next higher assembly. I think a lot of the environmental testing. There are things that we do as a routine that we have a lot of reliability data on, and do we need to run the same test over and over and over again? The question there is certainly up to you as to whether or not you want to expend the cost for doing some testing that really won't add any value. And again, a lot of this comes down to cost, lead time, and delivery. TRM is happy to go through and discuss your individual requirements with us very early on in the process to make sure that you don't overspec things. If you actually do need it, again, we are happy to do that. Just realize that there will be a cost associated with that. A really brief overview of Quantic TRM. Like I mentioned at the onset here, we are a provider of passive microwave components, DC to 40 gigahertz. We focus primarily on power dividers, directional couplers, hybrids, beamforming networks. We merge technologies as required for a lot of very custom sort of components. Happy to sell catalog parts as well. Although most of our customers do come to us for these very severe environments, highly integrated packages, as well as parts for unique environments, such as parts on a spacecraft. We also do some very high power stuff as well, integrated, a lot of integrated subsystems, and again, we like to work with our customers to make sure that the parts that they're getting are really parts that they need. And in there, it's a one-to-one relationship with our customers. We like to go out in the field, visit you, and then work with you to make sure that you get the parts that you need. Again, sort of iterating on there as well. What we do is we like to solve your problem. We like to work with you to make sure that what you have is indeed the exact solution for your individual problem. Whether that's a unique circuit design, whether it is a unique testing profile, whether it's a unique packaging, all of the above, or whether it's just a matter of supplying objective evidence in the line of data to make sure that the part does meet your requirements over your entire environmental range. A lot of the discussions today is maybe almost seems like we're sort of dissuading you from wanting to do that. That is not the case. We just want to make sure that you're aware that if you do require those things, it will be adding cost and it will be adding lead time. Again, we like to work with our customers. I personally like to go out and visit customers in the field to make sure that the parts that you're getting are really exactly what you need. The more we understand your problem that you're working on, the better, of course, we can go ahead and serve you to make sure that the part you're getting is exactly the part that you need. As Eric sort of alluded to, Quantic TRM is completely vertically integrated. We can build, design, manufacture, and test virtually everything that we do in our facility here in Bedford, New Hampshire. We have been providing these custom microwave solutions since 1970. So we've been doing this a long time. We're very familiar with the marketplace, and we love to support our customers.
Well, thank you very much, Sean and Eric. My name is Jason Jones. I'm the Director of Corporate Business Development for Quantic Electronics. Open up now to some questions if Sean and Eric will engage. First question here comes in. How can engineering prototypes achieve faster timelines while still requiring high reliability components for flight models?
Yeah, so oftentimes what we will recommend is if customers looking for EM models or engineering models for their devices on these high reliable products, that the components that go into that EM are similar to that of the flight. So if we're getting a set of resistors that are screened to an S level or a T level failure rating, for the EMs, we would use the same chip but at a lower rating or a more of a commercial rating to get them in faster at a lower cost so we can get prototypes out to you sooner. Same thing with connectors, right? If we're going to have full screen connectors for the flights, we can get that same connector just in a non-screened version to put onto the EMs to send those out quicker so that you have the parts at your hands faster for more benchtop evaluations.
Oh, awesome. Thank you. And encourage any of the participants in the audience, if you have any questions, excuse me, please feel free to ask them via the Q&A function for those that haven't already. A few more here in the queue. When specifying power combiners, is there any advantage to using different circuit topologies?
Yeah, I'll take that one. Yeah, absolutely. Basically, what we're looking at here with power combining, there's really a twofold problem that needs to be solved. One is the thermal and breakdown sort of design that is for the individual components. So we have to have enough thermal management so that the part does not overheat when you're looking at very high power combining, as well as you have to make sure that you don't have a breakdown issue. The other thing actually that comes up, which is very often overlooked, is the phase relationship between your input signals. And as that phase relationship begins to drift off of nominal, what happens is that because the power combiner works by combining vectors, some energy is actually subtracted and get dissipated into the isolation circuit of the power combiner. So as a result of that, we want to make sure that whatever we have where that energy is being redirected into the isolation circuit, that we always have a good thermal path from there down to ground. Now, a lot of devices that can be used as power combiners, like a Wilkinson power divider, for example, those resistors are actually in a balanced mode and do not have a good thermal path to ground. If you switch that around to a hybrid, you could then have a good 50 ohm termination going to ground for the balanced network, which now means that I have a much better thermal path, and I can now sink much more power through that path down to ground. So therefore, different topologies will have a different opportunity to being able to optimize that thermal path to ground, and therefore actually have it be able to handle more power, because you can get the heat out of it much more efficiently. So when you're looking at power combiners, there's certainly certain advantages to certain topologies over others. Sort of the flip side of that is when you get into a wider band sort of power combiner, that does sort of limit your choices. But again, this is a very big and important trade that really needs to be discussed and worked out to make sure that what you end up with is a part that will handle the power if for some reason your power combiner's phases start to drift on you, and making sure that the part can survive and be successful, and not end up with a part that's either way too large or too small.
Thank you very much, Sean. And one more question here. You didn't mention tapered line designs when reviewing the bandwidth trade-offs. How does that design approach compare with a traditional step transformer?
Okay, that's another good point there. I did not mention that. I probably should have. Taper line designs are used really when you're trying to get a very broadband sort of device. They are based, instead of being based on a traditional Wilkinson, which has a band pass sort of mathematical function, the taper designs have a high pass function, which means that there is a low end cutoff, and then they theoretically go on for much broader frequency up at higher frequencies. So for ultra broadband sort of components, this is the design approach that is typically taken. The downside of this device is that because you have to have an appreciable wavelength at the lowest frequency, by the time you get to the highest frequency that you're going to be operating at, there is a very significant amount of line loss that's associated with that. So for example, if you're trying to do a broadband part that goes from say 0.5 to 18 gigahertz, you can do that with a single taper line design. The taper line will be quite large, and therefore 18 gigahertz, your insertion loss is going to be quite significant. We do use taper line designs though for really higher frequency components. Once you get up into Ka band, for example, because the wavelengths start getting so short, having that longer transmission line to do that becomes a very good advantage, and you naturally get this extended bandwidth. So therefore, as you're working with the really higher frequencies, you do start using taper line designs as opposed to the band, the traditional band pass sort of design that you get out of a traditional Wilkinson. So again, there's a trade to be made here. Ultra broadband sort of components at the lower microwave frequencies, the insertion losses can be quite significant. As you get to higher microwave frequencies, because the part begins to shrink, the insertion losses become much more manageable at that point, and therefore that sort of topology becomes much more normal, as opposed to the bandpass sort of structures that you have at the lower microwave frequencies.
Awesome. Well, thank you very much, Sean. I want to take a moment to thank our panelists, Sean Moore and Eric Sumez at Quantic TRM. Thank our audience for joining us today. For those of you that joined late, we will post a recording of this webinar on our channel. And I want to invite everybody to stop by for more exciting critical insights with the Quantic Electronics team on our next Grid webinar scheduled for September 25th. More details about the topic will be out soon on that. And also invite everybody to visit quantictrm.com for more information on Quantic TRM, or to contact Sean and Eric as well. So thank you all for attending, and have a great rest of your day.